last video, we did our first example of using mathematical induction. In this video, we'll cover our second example of using mathematical induction. Again, it's super important to watch all of the previous videos about mathematical induction before just jumping into this one example. Otherwise, you're extremely susceptible to becoming confused, and I don't want that for you. Hey everyone, real quick, I just want to mention that this video is a part of a whole course that I made. You can find a link to this entire course in the description below, and make sure to click on that subscribe button. Alright, let's dive into our example for this video. We're going to prove that for all n, that's a natural number, 6 to the n minus 1 is a multiple of 5. So again, we're going to start by understanding the dynamics of the problem. What does increasing n do? Let's try a few examples. Let's start with n equals 1. Well, with n equals 1, we're looking at 6 to the 1 minus 1, which is 6 minus 1, which is 5, and that's a multiple of 5. Let's look at n equals 2. This is 6 squared minus 1, which is 36 minus 1, which is 35. Now, the goal isn't to just test every single natural number here, because that would take quite literally forever. So instead, to prepare ourselves for this proof of mathematical induction, let's take a look at what increasing n does and why this works. So instead of figuring out what 6 cubed minus 1 really is, I actually don't know. Instead, let's focus on what's happening here. So we're taking a number 36 and we're multiplying it by 6 to get 6 cubed. So we're multiplying a power of 6 by 6. Well, powers of 6s either end in a digit 6 or a 1. And so when you have some crazy number, 596, and then you multiply that number by 6, this first digit here is going to be a 6 when you do the multiplication. And likewise, if it's a 1 here, no matter what, your answer is going to have a 6. And so all powers of 6 are going to have either a 6 or a 1 in the ones digit, meaning that if you subtract 1, you get a multiple of 5. That's the essence of this proof, and now we're actually going to apply induction to show what this looks like. So let me erase everything, and then I'll show you the formal proof of induction. So here's the proof. We're going to let P of n be the statement 6 to the n minus 1 is a multiple of 5. So what do we start with? We always start with our base case. Base case, we can either technically do n equals 0, but I'm just going to do n equals 1, since that's the one we started with in this lecture. It doesn't really matter. They both work. And so let's check if P of 0 is true, or P of 1, excuse me. So we already did this. We already checked that 6 to the 1 minus 1 is a multiple of 5. So that's good. Let's work on the inductive step though. We're going to let k be an arbitrary element of the natural numbers, and we're going to assume P of k is true. Now, again, that does technically kind of look like we're assuming the conclusion here, but that's not quite what we're doing. Again, P of k is one instance of the statement, and we're assuming that one instance for that specific k value that's arbitrary in order to prove that the next case is also true, that P of k plus 1 is true. So we're assuming P of k in order to prove that P of k plus 1 is true, and that with the base case and mathematical induction will get us what our conclusion is here. So we're going to assume that P of k is true. That means that 6 to the k minus 1 is equal to 5, let me use a different letter here, j, for some j, which is an integer. Technically a natural number, but it doesn't really matter. Okay, so now we're going to try to prove P of k plus 1 is true. So we're going to now consider specifically 6 to the k plus 1 minus 1. Our goal is to show that this is a multiple of 5. Now we need to use the inductive hypothesis, which is that 6 to the k minus 1 equals 5j. And in order to do that, I'm going to write this as 6 to the k times 6 minus 1. And the reason I'm doing that is because I know what 6 to the k is. It's just 5j plus 1. And so this is 5j plus 1 times 6 minus 1. So see what I did there? Technically, if you want to do some algebra, you just add 1 to both sides to solve for what 6 to the k is there. And I can simplify this. This is 30j plus 6 minus 1, which is 30j plus 5, which is 5 times 6j plus 1. And here's the important part. We just now showed that this expression here is equal to this expression, which is a multiple of 5. And so we're done. And so by induction, P of n is true for all n in the natural numbers. Again, n greater than or equal to 1, technically, since that was our base case. However, P of 0 is also true if you started with that as well. It doesn't really matter. Anyways, thanks everyone, and I'll see you in the next lecture.